So now we move on to the thermal conductivity of a metal. So this thermal conductivity of a metal can also be derived with the help of classical free electron theory, right? So let us consider a conductor, right? So this is a conductor of we can say as a solid. So the length of a conductor that can be represented by the letter lambda, and we have two ends of this metal or a metallic conductor. Let be assigned A as a one end and B as a another end. So here we need to concentrate what happens the thermal conductivity of this conductor, how we can derive and in terms of expressions, right? So let me have assume the temperature at A or at end A can be represented as T, right? So and also we have an assumption at A is end A is maintained at higher temperature, and also compared to A, the end B which is maintained at low temperature as we have taken as T minus dt. So this is maintained at low temperature. So by the movement of electrons it acquires drift velocity. So we can have a current. In addition to that, there will be a thermal conductivity is also associated because of the movement of electron that is present inside a metal. And we know that heat can be flow from end A to B. So at end A, that is T, and B which is maintained at T minus dt. So the number of electrons per unit volume, number of electrons per unit volume is represented by the letter N. As you know already, the area of cross section is represented by the letter A. So before we get into the exact expression for this thermal conductivity, first we need to know what will be the amount of heat conduction through a conductor. So generally the amount of heat conduction can be represented by the letter Q. So the amount of heat conduction Q is directly proportional to area of the conductor and difference in temperature between the two ends. So for example, in general, we can say as theta 1 is maintained at one end of a conductor and theta 2 is maintained at another end of a conductor. So the difference in temperature is theta 1 minus theta 2, and definitely we need to concentrate the time taken. So initially one end is maintained at a hot end and another end is maintained at a cold end. So the heat can be flow from A to B, and definitely it takes some time. Okay, so that's why here time is one of the main parameter. And also we can say in general distance, or we can say as length of a conductor. So this is a general expression. When you remove the proportionality, we used to introduce a constant. Let we assign as K. Capital K is nothing but thermal conductivity. So which is multiplied by A, theta 1 minus theta 2 into T divided by X. The same expression can be written as, for our simplicity, we can write in terms of temperature gradient, Q is equal to K into A into d theta by dx into T. So this theta 1 minus theta 2 by x can be written as small change in temperature with respect to small change in distance, or we can say as length, right? And here we are taking a, for our simplicity, A is equal to 1 meter squared and time taken T is equal to 1 second. We can represent the amount of heat conduction per unit area per second as Q is equals to K into d theta by dx. So this is the very general expression for conductor. So now we are having a distance as or length as represented by the letter lambda, and also temperature we have a represented by the letter capital T, right? So that's why Here, according to our case, we can have K into d theta as a temperature dt by the distance or the length of a conductor is represented as lambda. So, this is the expression 1. Okay. So, and also we know that that is the it obeys classical free electron theory, or the movement of electron or the structure of an electron is same as analogous to the gas molecule that is present inside a conductor. Already we know that. Okay. So, that's why we can represent what will be the average energy. So, indirectly what you should understood is, because of the movement of electron, so we have a current. In addition to that, we have there will be a thermal conductivity. So, what happens due to that motion? What happens? The average energy acquired by an electron when it is at A. So, what will be the average energy at end A? Right? So, energy means that's kinetic energy. Whenever there will be a movement of electron, it acquires energy. That is, we can call it as a kinetic energy. So, that kinetic energy is same as that of kinetic energy of gases. So, I can represent the average energy at A is equal to 3 by 2 K into the temperature at end A is T. Okay. Same as that, I can able to represent what will be the average energy at B. Average energy at B. So, also 3 by 2 K into, here we have at point B, we have a temperature T minus dt. Right. So, and we know that the small k represents nothing but Boltzmann constant. Right. So, with that we can have a what happens, the excess of energy from A to B. Okay. So, we need to write the expression for what will be the excess of energy from A to B. So, that is why I have written. So, I know that what is the average energy at A, 3 by 2 K into T minus 3 by 2 K into T minus dt. Okay. So, this can be expressed as, so we can write like this, energy 3 by 2 K into T. So, when you multiply this minus inside a bracket, so what happened? Minus 3 by 2 K into T plus 3 by 2 K into dt. Okay. So, take our equation number 2 and 3. So, this is the equation number 4. So, what happens? These two terms gets cancelled. So, we have a remaining term K into dt. Put equation number 4. Right. So, with that we can have a excess of energy. Excess of energy, or we can say how will be the increase in energy. Anything you can write, increase in energy, or the excess of energy from A to B can be expressed as, in addition to that, we need to multiply this by the number of conduction electrons per unit volume. So, excess of energy, already we arrive at, in addition to that, that can be multiplied by number of electrons per unit volume and area. So, the number of electrons per unit area is equal to, we can write as 1 by 6 into n into V. So why we need to write this 1 by 6? So why we need to write this 1 by 6 is nothing but, so electron, it can be free to move in all directions. So we know that, so when you take this as a x direction, we have a positive x direction, and this is the negative x direction. And also we have, suppose if you taken y, this is a positive y and this is also negative y, and this is a positive z direction, and also we have a negative z direction. So because of the all the 6 directions, it can be free to move anywhere. So that's why here we have an expression 1 by 6 into n is represents as number of free electrons, V is a volume. So when you multiply it by these two parameters, we can get what happens, the excess of energy. So we can write excess of energy from A to B can be written as, so already we have an expression 1 by 6 n into, so wherever if you have written as V, please mention as drift velocity. So 1 by 6 n into Vd, which is multiplied by 3 by 2 k into dt. So what is the expression we are getting? 1 by 4 n Vd k into dt. So this is the excess of energy from A to B. Same way we can able to express in terms of from B to A, that is we can call it as a deficient energy. This is our excess of energy. This is we can say as a deficient energy from B to A. Deficient energy from B to A. Same as that, only difference is it is in opposite direction as that of this excess of energy. So just we need to introduce one negative sign. So that negative sign, it represents only the direction, it won't represent any value. So 1 by 4 NVD K into dt. So here we need to put one a negative sign. Okay. So what happened? The net amount of energy, net amount of energy from, net amount of energy is nothing but can be written as 1 by 4 NVD K into dt minus of, already we have one negative sign in that above expression. So let me assign as, this is the equation number 5 and this is the equation number 6 and equation number 7. With this equation number 6 and 7, we can able to write as minus of, here we have one minus here. So that's why I have put 1 by 4 n Vd, which is multiplied by k into dt. So what happened? 1 by 4 n Vd k into dt plus 1 by 4 n Vd k into dt. So how we can write? 1 by 2 n Vd k into dt. So this is the net energy from A to B. So put a equation number 7. So we need to relate this equation number 7 with the basic equation, as we know already. What happens is Q. So according to our case, we have a general expression, that is the amount of heat conduction from A to B. Q can be written as K, which is multiplied by dt divided by lambda. So here the length of the conductor as we have represented as lambda. So this is already we know, this is the equation number 1. Okay, so we relate these two, amount of heat conduction, or we can have a Q. So relate the equations 1 and 7 So k into dt by lambda, which is equal to, we have 1 by 2 n vd k into dt. Right. So when you relate these two expressions, this dt cancel. So we are trying to express in terms of k, because k is nothing but thermal conductivity. So we can arrive at the final expression, k is equal to 1 by 2, which is multiplied by nvdk into lambda. So as you know already with the basic definitions, lambda is nothing but mean free path. So we know that, so what is that? Vd is equals to lambda by tau c, right? So and also we can write as lambda is equals to Vd into tau c, right? So when you substitute over here, so what happens to the k? K is equal to 1 by 2 n Vd, which is multiplied by k, and also lambda can be represented as Vd into tau c. So we can write n Vd squared k into tau c. So this is the final expression for thermal conductivity of a metal. So with that expressions already we arrive at electrical conductivity, sigma is equal to n E squared tau c by m. This is also we arrive at already. So with the help of these two expressions we can prove Wiedemann-Franz law. So now I move on to the proof of that Wiedemann-Franz law. So Wiedemann-Franz law states that the ratio between thermal conductivity and electrical conductivity of a metal is directly proportional to the absolute temperature of a metal. So in statement we are telling the ratio between these two is directly proportional to the absolute temperature. So thermal conductivity is represented by the letter K and the electrical conductivity is represented by the letter sigma. So the ratio between these two is directly proportional to the absolute temperature T. So when you remove this proportionality constant, we used to introduce a constant that is represented by the letter L into T. So this L is nothing but Lorentz number. L is nothing but Lorentz number. Okay. So same as that we know the value of K and we know the value of sigma. Just to substitute over that we can get a value of L. So what is K? 1 by K by sigma 1 by 2, which is multiplied by n Vd squared small k into tau z, whole thing divided by, we have a sigma n E squared tau c by m. So just I substitute the expression for k and sigma over here. So what happens is n and n gets cancelled, this tau c gets cancelled. So the m, it will be moved towards the numerator. So 1 by 2 m Vd squared into k divided by E squared, right? So as you know already, so from the basic ideas it obeys the kinetic theory of gases. So we can write half m Vd squared as 3 by 2 k into T. So just I replace this m V squared. So what happens, this expression k by sigma is equal to, instead of m V squared, 3 by 2, which is multiplied by small k, k into T Already we have one k here divided by E squared. So just I rearrange this expression 3 by 2 k into k. So that's why I have a k squared by E squared, which is multiplied by t. Same expression can be written as k by E the whole squared into t. So we arrive at, from the statement, k by sigma is directly proportional to t. So that is, proportionality constant is L. So with that expression, L is equal to 3 by 2 k by E the whole squared. So this is nothing but Lorentz number. So we know the value of k. K is nothing but Boltzmann constant. So 1.38 into 10 to the power minus 23 joule per Kelvin or joule Kelvin power minus 1. E is nothing but charge of an electron, 1.6 into 10 to the power minus 19 coulomb. So when you substitute these two values to the above expression L, L is equal to 3 by 2, which is multiplied by 1.38 into 10 to the power minus 23 divided by 1.6 into 10 to the power minus 19 the whole squared. So we get the value of L as 1.12 into 10 to the power minus 8 watt ohm Kelvin power minus 2. So this is the Lorentz number. So we arrive at electrical and thermal conductivity of a metal by classical free electron theory. Hence we proved, with the help of the expressions k and sigma, with the help of Wiedemann-Franz law, we proved it, and also we get the constant value of Lorentz number as L is equal to 1.12 into 10 power minus 8 watt ohm Kelvin power minus 2. Hence we conclude, so this theory, the classical theory, is well in agreement with both the theoretical and experimental value, but it is applicable. What are the main drawback for this classical free electron theory? As only it is applicable at low temperature, or when you are maintaining a metal at normal temperature, or we can say as room temperature. It is applicable only for low temperature, and it is mainly depends on the electrical conductivity and thermal conductivity is mainly depends on, or it is directly proportional to the number of free electron that is present inside a metal. Thank you.